Paragraph 1. The history and impact of Mount St. Helens. Mount St. Helens is one of the most iconic volcanoes in the United States, known not only for its devastating eruption in 1980 but also for its significant role in advancing the field of volcanology. It is located in Washington state in the Cascade Range, an area that is geologically active due to its position along the Pacific Ring of Fire. This stratovolcano, characterized by its conical shape and explosive eruptions, has been an object of fascination for scientists and the public alike. The eruption on May 18, 1980 was the most catastrophic in U.S. history, and it had profound effects on the region. Prior to the eruption, there were early warning signs, including earthquakes, steam venting, and ground deformation. Yet, no one could have predicted the magnitude of the eruption, which began with a massive landslide followed by an explosive lateral blast that leveled entire forests, sent ash plumes 15 miles into the atmosphere, and affected air travel across the United States. The eruption of Mount St. Helens caused widespread destruction to the environment and disrupted the lives of thousands of people living in the surrounding areas. Approximately 230 square miles of forest were flattened and rivers were clogged with debris, leading to flooding in the surrounding valleys. The ash cloud from the eruption covered large parts of the country, including several major cities, and even affected the global climate for a brief period. This event had long-term ecological consequences, including the displacement and extinction of local wildlife species, destruction of vegetation, and the alteration of the region's landscape. However, while the eruption caused immense destruction, it also revealed a great deal about volcanic activity, and scientists have since used Mount St. Helens as a case study to understand how volcanic systems function. The eruption was a significant moment in both geological history and disaster response, underscoring the unpredictability of nature's power and prompting further study into volcanic behavior. Since then, Mount St. Helens has continued to be an active area of scientific research. Over the years, the region around Mount St. Helens has seen remarkable ecological recovery. The resilience of life in the wake of such catastrophic events demonstrated the incredible power of nature's regenerative abilities. Within a year after the eruption, life began to return. Plants like lupins took root in the ash-laden soil, enriching it with nitrogen. Small mammals, insects, and birds returned as well, finding niches in the new ecosystem that was slowly developing. Scientists have studied the area extensively, noting how the dynamics of ecological recovery and the role of different species in this process have reshaped our understanding of how ecosystems can regenerate after volcanic events. The explosion not only changed the landscape but also the way we think about environmental resilience, providing key insights into how life can spring from devastation, an outcome that was not widely anticipated. Understanding this regenerative process is crucial for anticipating future eruptions and preparing the world for similar volcanic events. Paragraph 2. Modern seismic activity and indicators of recharging. Mount St. Helens has not been dormant since the 1980 eruption. Recent scientific studies have shown that the volcano is once again becoming active, with a noticeable uptick in seismic activity. Between late 2019 and early 2020, over 350 small earthquakes were recorded around the volcano, marking the highest level of seismic activity in the area in years. While these quakes are generally low in magnitude, their frequency and distribution suggest that magma is moving within the volcano system. These are known as earthquake swarms, and they are often precursors to more significant volcanic activity. These minor earthquakes result from the shifting and fracturing of the Earth's crust under the immense pressure exerted by rising magma. Such movements are natural during the recharging phase of a volcano, when magma slowly ascends toward the surface over the course of many years or even decades. Scientists have been closely monitoring these swarms of small earthquakes as they can offer crucial information about the ongoing processes beneath Mount St. Helens. These quakes occur at shallow depths, which means they are likely caused by magma pushing upward from deeper reservoirs. This shift in seismic activity is a clear sign that Mount St. Helens is not as dormant as it might seem. Ground deformation is another key indicator of volcanic recharging. In recent years, satellites have detected slight but consistent uplifting and tilting of the ground around the volcano, which further suggests that magma is accumulating in the chamber beneath the surface. Such ground shifts are crucial for researchers to track, as they can provide a tangible sign that volcanic pressure is building, which might eventually result in an eruption. In addition to seismic activity and ground deformation, increased gas emissions are also an important indicator of volcanic recharging. Mount St. Helens has been emitting higher than normal levels of carbon dioxide and sulfur dioxide, gases commonly released when magma ascends toward the Earth's surface. These emissions provide researchers with valuable information about the depth and composition of the magma chamber beneath the volcano. Elevated levels of sulfur dioxide, for instance, suggest that magma is rising closer to the surface, which could mean that the volcano is approaching a more active phase. While these emissions do not guarantee an immediate eruption, they serve as a vital warning system that scientists use to predict future volcanic activity. All these indicators, the seismic activity, ground deformation, and gas emissions paint a picture of a volcano that is slowly recharging and that, in time, could become more volatile. Paragraph 3. The process of recharging and implications for the future. The recharging phase that Mount St. Helens is currently undergoing is a slow and gradual process. During this phase, magma from deep within the Earth's mantle begins to rise through the crust, where it accumulates in a magma chamber beneath the volcano. This process can take anywhere from several years to several decades, depending on a variety of factors including the volume of magma and the rate at which it rises. As magma moves upward, it exerts pressure on the surrounding rock, causing fractures and faults in the Earth's crust. These fractures can result in the earthquakes that scientists are now observing. As the magma chamber fills and pressure increases, gas bubbles trapped in the magma are released, contributing to the gas emissions observed around the volcano. Importantly, the recharging phase does not necessarily mean an eruption is imminent. Many volcanoes, including Mount St. Helens, can remain in a recharging phase for years or even decades without erupting. For instance, after the 1980 eruption, the volcano spent several decades in a state of relative quiescence only to show signs of renewed activity in the late 2000s. This underscores the unpredictable nature of volcanic systems and the challenges scientists face in predicting when, or if, a volcano will erupt. While the recharging phase is a natural and necessary process for a volcano's long-term activity, it also serves as a reminder of the inherent dangers posed by these dynamic geological systems. Monitoring a volcano in the recharging phase requires sophisticated tools and techniques, as small changes in seismic activity, gas emissions, or ground deformation can serve as critical signals of future eruptions. The consequences of a future eruption of Mount St. Helens could be significant depending on the size and type of eruption. If the volcano were to erupt in a manner similar to the 1980 explosion, the surrounding areas would once again face devastation. The landscape could be reshaped by pyroclastic flows, ash clouds, and lava flows, while infrastructure, forests, and wildlife would suffer extensive damage. Communities living near the volcano would be at risk, and the environmental consequences would likely last for years or even decades. However, it is also possible that a smaller, more effusive eruption could occur, one that would have a less catastrophic impact on the surrounding landscape. Regardless of the specific outcome, scientists agree that continued monitoring of Mount St. Helens is essential to understanding the timing and nature of any future eruptions. The lessons learned from the 1980 eruption and subsequent studies of volcanic recharging processes have helped to refine prediction models, which will be crucial for minimizing the impact of future eruptions. Paragraph 4. The role of technology in volcano monitoring and global implications. The study and monitoring of volcanoes like Mount St. Helens have greatly benefited from advancements in technology. In the years following the 1980 eruption, scientists developed new tools and methods to more accurately track volcanic activity and predict potential eruptions. One of the key developments has been the use of satellite imagery to observe ground deformation. Satellites equipped with synthetic aperture radar (SAR) can detect even millimeter-scale changes in the Earth's surface, providing precise data on the movement of the ground around the volcano. GPS stations have also become an invaluable tool as they allow researchers to monitor shifts in the Earth's crust in real time. These technologies, coupled with traditional seismic monitoring equipment, provide a comprehensive view of volcanic activity, enabling scientists to make more accurate predictions about future eruptions. Additionally, modern gas measurement techniques have allowed for more detailed analysis of volcanic emissions. Instruments that measure the composition and volume of gases like sulfur dioxide and carbon dioxide provide valuable insights into the depth and movement of magma beneath the surface. These gas measurements can help researchers understand the volcanic system's internal processes and gauge the likelihood of an eruption. With the combined power of satellite imagery, seismic data, and gas analysis, scientists are now able to track the recharging phase of Mount St. Helens and other active volcanoes with a level of detail and accuracy that was not possible in the past. These advancements have significantly improved our ability to predict volcanic activity and mitigate the impacts of eruptions on human populations and ecosystems. The implications of these advances in volcanic monitoring are far-reaching, not just for Mount St. Helens, but for volcanoes around the world. With volcanoes posing a threat to millions of people worldwide, the ability to predict eruptions more accurately is crucial for saving lives and minimizing property damage. As the global population continues to grow and as more people live in close proximity to active volcanic regions, effective monitoring and early warning systems will become increasingly important. In this context, the research and technological developments that have come out of the study of Mount St. Helens could serve as a model for volcanic risk management worldwide. By continuing to refine these monitoring techniques and sharing this knowledge with other volcanic regions, we can improve global disaster preparedness and reduce the risks associated with volcanic activity.